Both panels show the same Google search request, but the answer on the right starts writing sooner because it uses speculative decoding. A smaller language model proposes several tokens, and the main language model checks those tokens together in one pass. The main model still checks every proposal, but that one pass can produce several accepted tokens instead of only one. To see why this saves time, we need to examine the work that the main model performs to produce one token. To produce that one token, the main model uses the prompt and all tokens already selected, processes the current position through every model layer, and calculates a score for every possible next token. With greedy decoding, it selects the token with the highest score and adds that token to the input for the next pass. The next pass cannot start before this selection because it needs the selected token as part of its input, so a response with 100 new tokens needs about 100 sequential passes through the main model. After the prompt is processed, the key value cache stores attention data for the positions that the model has already processed, and each later pass reuses this data instead of calculating it again. The cache removes repeated attention work, but each new token position must still go through every model layer, which requires the hardware to read the weights for every layer from memory. For one request, each pass applies those weights to only one new token position, so the processors finish using available weight values faster than memory can supply the next values. When moving the weights takes longer than using them, memory bandwidth determines the time for the pass, and the main model pays this cost again for every new token. The hardware could apply each set of loaded weights to several new token positions during one pass, and perform more useful work for each weight read, but ordinary decoding cannot provide those positions because it must select one token before it knows the input for the next position. This is where the smaller model helps by supplying candidate tokens for these unknown positions, which gives the main model several positions to check together. The smaller model has now placed the temporary candidate's fox jumps into the, after the verified prefix the quick brown, so the main model has an input token at every position that ordinary decoding could not fill in advance. The smaller model is the draft model, and the main model is the target model that still makes every final token choice. The target uses only the quick brown to calculate its choice for the first position, then it uses the quick brown fox for the second position, and it continues in the same way until it uses the quick brown fox jumps into for the fourth position. The causal attention mask makes each position use only the tokens to its left, and because all four left-hand sequences are already present, the target can calculate all four choices together in one pass. This pass does not add any candidate to the verified answer, because each candidate remains temporary until it matches the target choice for the same position. If the first two candidates match, but the target selects a different token at the third position, the calculation for the fourth position used a token that the target rejected. So where must verification stop? The turning target card now reveals over while the third draft candidate is into, so verification must stop at this position. To see what the system can keep before it stops, move back to the first draft candidate and compare each candidate with the target choice for the same position from left to right. The first candidate is fox, and the target also chose fox after the verified text, the quick brown, so the system adds fox to the verified text. The second candidate is jumps, and the target also chose jumps after the quick brown fox, so the system adds jumps. The third candidate is into, but the target chose over after the quick brown fox jumps, so the system rejects into and adds over, which is exactly the token that ordinary greedy decoding adds at this point. The system also rejects the later candidate, the, because the target calculated its choice from a prefix that ended with the rejected word into, and that calculation cannot be used after over replaces into. In each cycle, verification keeps the consecutive draft candidates that match from the first position, then it adds the target choice at the first mismatch and rejects every remaining candidate. If all four candidates match, the same target pass also gives the target choice after the fourth candidate, so the system can add all four candidates and this extra target token. This procedure is greedy speculative decoding. The draft model proposes temporary tokens, the target model evaluates the complete proposal in one pass, and verification adds only matching draft tokens and a target choice. So every added token is the token that ordinary target greedy decoding would choose from the same verified text. One target pass can now add several verified tokens instead of one, but producing and rejecting draft candidates also takes time. So the next question is whether fewer target passes save more time than this extra work costs. In the cycle we just saw, one target pass checked 4 proposed positions and also calculated the target token after them, while ordinary decoding would need one target pass after another to reach the same position. The speculative cycle adds draft model work and makes the target model do more arithmetic, so it can be faster only if this added work takes less time than the separate target passes that it replaces. During one ordinary target pass, the hardware reads the target model weights from memory and applies them to one new token position, but during verification, it reads the same weights and applies them to several proposed positions together. With one request and low server load, moving the weights and waiting for communication can take longer than the arithmetic for one position, so some arithmetic units wait for data. The proposed positions use these waiting units and reuse the key value cache for the verified prefix, which lets the target model check a short group in only slightly more time than one ordinary pass. The full cycle still takes time to run the draft model, verify the proposed positions, update the caches, schedule the work, and communicate between devices, so speculative decoding is faster only when the tokens that pass verification save more target pass time than these added operations use. In one measurement from the original paper, an 11 billion parameter T5XXL target model used a 60 million parameter T5 small draft model for greedy translation with a batch size of 1-on-1 TPU v4. In this setup, speculative decoding generated tokens at 3.4 times the ordinary decoding rate, which shows that the saved target passes outweighed the added work under these specific conditions. This result used arithmetic units that would otherwise wait, so what happens when other requests already use those units? Those 4 candidate positions used arithmetic units that would otherwise wait, but when the server processes many requests together, those requests already use the same units, so the candidates must compete for processing time. The number of requests that the target model processes together is the batch size, and each request adds one ordinary next token position before speculative decoding adds any candidate positions. With a batch size of 1, the 4 candidates can use inactive arithmetic units, but with a batch size of 128, the ordinary positions already keep more units active, so the candidates make verification longer or reduce how many requests the server processes in the same time. A 2026 production study measured this effect with Eagle Llama 3.18b and GSM 8K, where the speedup fell from 1.73 times at a batch size of 1 to 1.21 times at a batch size of 128. The candidate count creates a second limit, because a short draft can stop while more matching candidates were possible, but a long draft can spend time on candidates that the target cannot use. For example, if the second candidate is the first mismatch, the third and fourth candidates depend on that incorrect token and cannot become output, although the draft model created them and the target model verified them. Because the position of the first mismatch changes during generation, the runtime can increase the candidate count after repeated matches, decrease it after early mismatches, and decrease it again when the batch size grows. Counting matching candidates does not show the complete speed, because a longer draft can produce more matches while its added drafting and verification time makes the complete cycle slower. Speculative decoding helps only when the complete cycle produces verified output tokens faster than ordinary decoding after the system includes drafting, verification, cache updates, scheduling, and communication. The next question is, what should generate the candidates fast enough and accurately enough for the accepted tokens to save more time than the system spends creating and verifying them? The original method can use the 60 million parameter T5 small model to generate candidates for the 11 billion parameter T5XXL target model. Starting from the verified text, the smaller model predicts candidate tokens one at a time from left to right, and the target model then verifies the completed group in one pass. This method increases speed only when the target passes that it replaces take more time than the added draft work, and the system must also store the smaller model weights and a second key value cache. Prompt lookup removes the smaller model and searches the prompt or generated text for an earlier occurrence of the recent token sequence. When it finds a match, it copies the tokens that followed the earlier occurrence into the candidate positions, which costs little and works well for repeated texts, such as code, but gives no candidates when no sequence matches. The target model itself can also do some of the candidate work. LayerSkip stops at an early target layer, uses the output at that point to predict a candidate, and then uses the remaining layers to verify that candidate. Medusa connects small output modules to values that the target model has calculated for the current position, and these modules predict tokens at later positions. Eagle uses values that the target model has already calculated to predict the value or token for the next position, while native multi-token prediction adds a built-in module during target model training so that the module can predict several later tokens. These target-based methods can still have a serial delay when they generate candidates from left to right, because each candidate must exist before the next prediction can begin. DFlash removes that delay by filling several blank candidate positions in one draft pass, and by using values from the target model to improve those predictions, after which the target model applies the same left-to-right acceptance rule. In reported Quinn3-4b tests, this shorter draft step made complete generation faster than Eagle 3 on some tasks, even when DFlash produced a similar or lower number of accepted candidates. A smaller model, repeated text, calculations from the target model, or one parallel draft pass can therefore fill the same candidate positions, but the target model still decides which candidates become output, and 3 measurements determine whether the method saves time. To compare these 4 candidate sources, measure the time to generate one candidate group, the number of candidates that match the target model's tokens, and the time needed to check the group under the current server load. These measurements cover one complete cycle in which the source generates candidates, the target model checks all proposed positions in one pass, and the system compares the candidate tokens with the target model's tokens from left to right. The system keeps each matching candidate and the target token at the first mismatch, then discards all later candidates. So the final output is the same as ordinary greedy decoding. Speculative decoding saves time only when this complete cycle finishes before ordinary decoding can produce the same output with sequential target passes, which is more likely when candidate generation is fast, many candidates match, and the current hardware checks the group quickly. The Google search answer on the right can therefore begin sooner while the target model still decides every output token, because one target pass can confirm several tokens instead of producing only one.